Testing, testing, 1, 2, 3, testing, testing. Testing! 1, 2, 3. Did my video seriously freeze again? Absolutely ridiculous. Okay. Can I save that setting? Alright. Anyway. Hello! Good morning, all of you fine people out there in television land. I am your professor for Computer Science 1MD3. Perhaps we have some people joining us today who didn't quite make it to the lecture yesterday. Perhaps not. Perhaps we'll see what is typical with university classes, an exponential decline in viewership as the semester wears on. Hopefully we can get things up, you know, keep things up at the first week. Can still hear me though. It doesn't super matter if the camera freezes, so long as you can still hear my voice. My voice is the important part. The camera is just to capture my overly enthusiastic gesticulations. Yes. There we go. Question: are the tutorials going to be recorded? Answer: yes. Moving on. Yeah, the tutorials are going to be recorded. I think the way that it works with MS Teams, and it looks like all the tutorials are going to be over MS Teams. Record this thing button sends the video to Microsoft Stream, which is a separate thing. And so the tutorials, in theory, will be available after the fact. We shall make those sufficiently accessible for you guys. Won't we, Mark? Hello, Mark. Good morning, Mark. Yeah, so, that's good so far as it goes. So, we might as well get right into our lecture material today, seeing as, you know, we've got a little bit left to do. We were talking about this final example. Ooh, I forgot to post this this code, didn't I? Oh well. Might as well post the completed code. So, let's see here. So we had this example where we were finding the minimum and maximum of a series of numbers. Now, you'll find that as things progress in this course, more and more of the problems that you will be expected to solve will involve collections of data. This, in particular, is called a list, which is distinct from a tuple, set, dictionary, and string, which are the other four types that we're going to get into. We'll talk about them all in depth when we talk about topic 4. Until we cover topic 4, you're kind of not... We'll cover things a little bit as we get into the end of topic 3, etc. But in general, you should have as a firm goal in your mind being able to work with collections of data effectively within the context of a program. Towards the end of the course, like, pretty much all the questions are going to involve collections of one type or another. This, in the same way that pretty much all of the questions will require loops and if statements. That's the thing that that's one of the things I tried to hammer home last time in class, was the first 4 topics in this course are absolutely crucial to your understanding of the entire rest of the course and the entirety of any programming that you may do in the future. They're like the basics of the basics. If you don't understand this, then you're going to have a tough time on the exam. So anyway, just to quickly recap this guy. This was an algorithm for going through a collection of things, finding the minimum and maximum, and then returning them. So the way that this algorithm works, we set minimum and maximum to the first element in our collection of data, designated item 0, because collections in programming languages start numbering things at 0 for reasons that have to do with programming and stuff. And we also assign a loop variable I. So long as I is less than the size of the data collection, herein designated by T, formal parameter is T, actual parameter is X. We'll get into the difference between formal and actual parameters a little bit later on. Topic 5. If the particular element that we're examining, Ti, is less than the currently recorded minimum value, we overwrite that value with that value Ti. Otherwise, we perform essentially the same check, but with the maximum. We check to see if the the element of the data structure, which is currently being examined, T at I, we see if that's greater than the currently recorded maximum. If it is, then we overwrite the currently recorded maximum with the currently examined element of the data structure. Once we have performed those checks, it is necessary that we should modify I so that we can look at the next element in the data structure on the next loop iteration. If you leave this guy out, then you will be examining the same element of the data structure forever. You will get yourself into an infinite loop. Infinite loops are infinitely undesirable, so I recommend trying to avoid them at all costs. And then, of course, once all of that has been done, once we have traced through each element of the data structure and performed these checks on them, we can be reasonably sure that whatever the minimum and maximum are after this loop, those are the actual minimum and maximum that exist inside of the data structure, because we have effectively compared every single element in that data structure to every other element in that data structure. And through that process, we've found the minimum and the maximum. So then we return the minimum and the maximum. So there you go. Algorithms. Let's see here. How do we know how many indentations to use? Very good question. Very good question. I'll take this one. So So this is kind of getting into the nuts and bolts of programming in Python. For those of you who have programmed in other languages and are now taking this class, I don't know if you guys did like Java or C, one of those languages in high school or something. Other languages will use curly braces to designate things that are inside of other things. So in a language like C, all of the stuff that's inside of the while loop is designated as inside the while loop by being inside of this set of curly braces. In Python, that semantic content, that is to say, that distinction in the programming language is determined by the level of indentation rather than specific bracket characters. This is the way that Python chooses to convey that information, right? Or it's the way that Python chooses to force you to convey that information, shall we say. So the fact that this statement, this statement, this statement, this statement, this statement, and this statement are all at indentation level 2 or higher means that all of these statements exist within this while loop. So it's correct to think of the statements as occurring in blocks, right? This block exists within this function definition. This block exists within this loop. This block, and it is a block, although it only has one statement, exists within this branch of the if statement. This block exists within this branch of the if statement. You can tell that this I plus equals 1, is not inside of any of these if statements because it's at the same level of indentation as the if statement itself, right? This is outside of all of the if statements, but inside of the while loop because of the level of indentation it occurs at. It's kind of something you'll have to just get a feel for. That's one of the trickier things with programming in Python. Unfortunately, in my opinion, it's one of the things that makes it's something that's harder to pick up on in Python than it is in another programming language like C++ or Java, because you don't have a character specifically and explicitly designating a block of code as being inside of something else. It's done implicitly through indentation level. But that's a very, very important thing to know about when you're programming in Python. So, good question. Thank you. Yes, I plus equals 1 is part of the while loop. So, good. Wonderful. Cool. So, I'm just gonna skip those slides because they're not very interesting. Essentially, what's the minimum number of comparisons when n is equal to 3? How many, like, if we were to go through them, how many times would we compare one thing to another thing? Of course, this, this slide forgets the fact that the loop comparison itself is also a comparison. So the fact they're looking for the answer, I think 2, and they're gonna actually end up with 4. So so be it. The going through of an algorithm and measuring the number of instructions it takes on one path versus another, this gets at the problem of analyzing the effectiveness. Well, not efficiency of an algorithm versus the correctness. A correct algorithm may have any number of instructions included in it, and many of those instructions may be redundant. A solution which is correct is not necessarily one which is efficient. Although, as I said in the previous class, you have to sort of hit some baseline level of efficiency for your algorithm to actually terminate. It has to, for example, not have an infinite loop in it. So, you know, it has to be executable to be correct. That's another way of saying that. But in general, in this class, you're not going to be marked on the efficiency of your code. You're going to be marked on whether or not your code produces the correct answer. And the reason that we take that approach with programming is programming is a skill. And similar to many other skills that you may want to pick up in your life, like playing a musical instrument or doing martial arts or something like that. I'm going to pick martial arts as an example because I think the analogy is a little bit more direct, oddly enough. When you're first learning martial arts, a good teacher will give you the room to make your own mistakes, right? It's by the process of making your own mistakes and then correcting them that you really learn how the martial art that you're learning works, right? Same thing with learning a musical instrument. If you, practicing your scales is all well and good, but you have to pick up on the mistakes that you make when you're learning a piece, right? And you have to make the mistakes and you have to correct your own mistakes, and it's by correcting your own mistakes that you'll become a better musician, right? So coding is no different. In this class, you really should think about this as a problem-solving class. We are going to give you problems and expect you to come up with solutions to them. In this class, you're not going to learn a set of rigidly defined structures that are applicable to specific problems. That's the way that a normal math class works, most of the time. It's like, I'm learning differential equations. I learned this method, I learned that method, I learned this method for dealing with this type of problem, that type of problem, that type of problem. You learn an algorithm, and that's essentially what a math class is you're learning algorithms for solving specific types of problems. Coding is different. In coding, you're learning how to create the algorithm that solves the problem, because that's the useful skill in programming. So, when we give you a problem, we will often specify that problem in terms of the inputs that it receives, the inputs that your function receives, and the outputs we expect from the function. All of the middle bit is left up to you to come up with. So we don't expect you to come up with, the world-class efficient solution to any particular problem, because that's quite a lot to expect of any undergraduate, even one in computer science, right? And many of you guys are not from computer science. So, it's kind of unreasonable for us to expect you to come up with, the most efficient solution to any particular problem ex nihilo. It's kind of like expecting a seventh grader to come up with Pythagorean theorem. It's like just not possible in most cases, So you're allowed to come up with inefficient solutions. The hope is that as you become better and better at programming, as you realize where the redundancies are in the code that you write, or as you realize the type of code that's likely to lead to problems, you'll sort of tune up your programming skill and eventually refine it so that you can program more and more effectively. But this is a skill that takes a long time to develop. And, you certainly won't be finished with the development of that skill by the end of this class. So, anyway, that's sort of the general philosophy. That's a lot of... My goodness, that's a lot of... Thank you, Mark, for answering all these questions. That's a lot of questions. So, a lot of the questions that you're asking in the chat are things specifically related to syntax, which we're going to be covering in depth in Topic 2. So, Don't worry if you don't get this stuff immediately. These examples are primarily to give you the flavor of the language rather than, like, we're not drilling down on the specific syntactic details just yet. Although, if you're picking up specific syntactic details from this overall sort of more higher level description, that's also a good thing. So let's talk a little bit more about programming in general. So, what is a program? You guys should probably already have a reasonable idea of what a program is. A program is an algorithm that is executed automatically by a computational device. Fixed program computers serve only one purpose. These days, most fixed program computers that you'll find are electronic devices, like small electronic devices like kitchen timers or washing machines or something like that. These are devices that have one program. They execute only that program, and they can't be reprogrammed with a different program. That's because the program itself is etched into the electronic circuits of the device or stored in some, non-overwritable memory cell somewhere on the circuit board. Generally speaking, when we think about computing devices, we're talking about stored program computers. These are devices that store their programs in overwritable memory, so the programs can change over time. And this is anything from your laptop, cell phone, tablet. I don't know if people are still using tablets. Your Nintendo Switch device. Any number of things. Incidentally, the Nintendo Entertainment System was a fixed program computer because the programs themselves were etched onto circuit boards, which are what are contained inside of those cartridges that you have to slot into the machine. The device itself doesn't actually store anything in impermanent memory, right? Unless it's like one of those advanced circuit boards that has this save system in it, but the overwhelming majority of Nintendo games, original Nintendo games, weren't capable of saving data, which makes them fixed program that makes it a fixed program computer most of the time. So, the way that you achieve a stored program computer, and I talked a little bit about this when I was talking about Alan Turing yesterday. If you store the program in the same way that you store the data that you operate over, then the program itself can become data that you operate over. So a computer which is capable of modifying its own program. This is the idea of a universal machine, which was laid out by Alan Turing in 1936, and subsequently the idea was then used to build some of the very, very early computers, like the Manchester Mark I. And if any of you have seen The Imitation Game, which is a movie that came out a few years ago, featuring everybody's favorite actor, Benedict Cumberbatch. Very good movie if you're into computers and stuff. Very interesting movie. So that's fine. So that's what a computer is, more or less. In this class, because this is computer science and not electronics, this is not a class on electronics, so we're not particularly interested in the exact mechanisms, like the exact electronic mechanisms by which memory is stored, or stuff like that. We are interested primarily in the properties of computers and how they, we'll be dealing primarily in high-level abstractions of how computers work, rather than the nitty-gritty of the individual, AND gates and stuff like that. If you're interested in that sort of stuff, I highly recommend taking classes on electronics. But basically, that's we're not going to be talking about the physics so much. So the overwhelming majority of computers that you will be using in your daily life they all use the same style of processing architecture. When we say architecture in the context of computing, what we're saying is the manner in which the computer has been assembled, essentially, or the manner of its operation. This abstraction here is a computer architecture. So, in general, and this kind of goes back again to your grade school studies of computers, when you talk about computers, you're primarily talking about three things, right? You're talking about input devices, the processing unit, and output devices. So, in terms of physical devices, input devices are things like your keyboard, your mouse, your webcam, your microphone, etc., etc. Output devices are things like your monitor and your printer and your speakers. And, if you've got a desktop computer, this box here is kind of your tower unit as a whole. The input devices and output devices are all plugged into this thing. Within the computer itself, we've got, we can break that organization down a little further. So we have the central processing unit, or CPU. Generally speaking, most of the computers that you'll use in your life have a central processing unit, or CPU. And they'll have a memory unit. So that's the main distinction for us, is between processor and memory. Within the processor, there are various subsystems that control things like controlling the flow of commands through the processing process, kind of a clumsy way of saying it. And then you have the part of the CPU that actually performs arithmetic or logical operations on data. So the correct way to think of a computer is as a machine that performs arithmetic or logical operations on digital data. Everything else is just, so much wrapping paper. The control unit, the only purpose of the control unit is to ensure that the correct commands are being executed in the correct order at the correct time. The whole purpose of the memory unit is to enable the storage of data between the execution of operations. We'll get into it a little bit, but if you take a look inside, like in the deep levels of a CPU, you actually have a reasonably small number of operations. Each command that a CPU is capable of executing is actually an individual circuit inside of the CPU itself. And, depending on which command is requested, different circuits are used to, operate on the particular data at hand. But, so in general, input, processing, output, there's a distinction between the processor and the memory. Understanding how memory works and understanding how instructions work, once you have those two things, you can program pretty much any language. Everything after that is just syntactic differences. Or, semantic differences. At least it's applicable to imperative languages, at least. If you're talking about stuff like Haskell, which is a little bit more exotic, then things start getting different, but it's still useful to know how memory works. So, CPUs and machine language. CPUs operate on bits, zeros and ones, grouped into words, typically 32 or 64 bits in size. The modern computer system operates on 64-bit words. If you take a look at your you know, the stickers on your laptop and one of them says 64 bits, then you know you have a 64-bit operating system, though that's that's assumed most of the time these days. Yes. So all computer memory occurs in ones and zeros. In the underlying electronics, that corresponds to low and high voltage, 0 volts and 5 volts. The electrical potential it operates on transistors, which are tiny little bits of semiconductor inside of the CPU and other parts of the computer. And when I say tiny, I mean very, very, very small, like beyond microscopic. At this point, transistors, the thickness of transistors inside of a CPU can be measured in terms of the number of atoms they are across. That's where we are with electronics these days, which is kind of crazy if you think about it, because these things are everywhere, right? But anyway, CPUs are like the most complex thing that human beings have invented so far, and most complex physical object. So, CPUs within themselves contain their own very limited memory called registers. Basically, in order for a CPU to operate on memory, operate on data, that data has to be loaded into the CPU itself. And when it has been loaded into the CPU, it is stored in temporary memory called a register. So the main operations that CPUs perform are loading data from main memory into registers, performing arithmetic operations on the data that's inside of registers, storing data from registers back into the memory, and jumping around from one instruction to another based on the values in registers. So, one quick note on the way in which computers operate in terms of programs. If you remember the Python tutor, there we go. Let me just load up this program. So, you know how this, you have these arrows, right? And how these arrows jump around. You can think of it this way. Think of the program as a list of instructions that the CPU is looking at. One of the pieces of memory that the CPU keeps track of is what instruction it's on. That is what the green arrow is here. That's what instruction you're on. All that these control flow constructions, if statements, while loops, for loops, branches, and if statements, all that these things do is they manipulate what instruction is being pointed to, right? They manipulate what instruction you're on from the CPU's perspective. They allow you to skip segments of code, come back to segments of code, choose one segment of code instead of another, and all of this physically manifests in the value of what instruction you're on. Roughly speaking, what line of code you're on here, although each one of these instructions actually constitutes several CPU instructions. What line you're on jumps around, and that is the entire point and purpose of the control flow commands. In fact, functions, like defining a function, does the same thing. You define a function, that's fine. Whenever you use a function, that causes the program pointer to jump into the definition of the function itself, execute the commands in the function, and then when it's finished, return to the point in the program where that function was called. It's very, very important to know that a computer only executes one instruction at a time. Cool. Oh, you're taking 1xc3 next semester? I'm teaching it, so I'll see you next semester. Oh, is my camera frozen again? Jesus Christ. All right. As long as the audio doesn't cut, that's the main thing. I wish I could figure out what to do about that. Yeah, so 1xc3 is a course on C programming. C programming because C is a language that's much, much closer to the machine level than Python. These types of, like, if this type of topic is interesting to you, I recommend taking a course in C programming, because you'll have an opportunity to explore, how memory works in much greater depth. So anyway, let's talk about programming languages themselves. Programming languages have also seen a fair amount of development over the years. The original programming languages, once we had actually gotten to programming languages and we had gotten away from a computer only executing one program, which was, the fixed program computers of the 1940s and 50s. Once we got into programming languages, we started seeing languages like Fortran. Fortran stands for Formula Translator. This right here is a computer punch card. It used to be that if you wanted to write a program for a computer, you would have to do it on punch cards. You would have a deck of cards that you would take a little hole punch, and you would punch out all of the individual holes that you wanted that would correspond to commands and values, and you would take your stack of punch cards and you would feed it into the machine. The machine would slice through all of your, well, it wouldn't physically damage them, I hope, but it would run through all of your punch cards. It would run through the commands on all of your punch cards, and jump back and forth between your stack of punch cards, and then you would get like a little ticker tape output with like something in binary, and that would be the result of your computation. God help you if you ever dropped your stack. Hopefully you had written the number on each one, so that if they ever got out of order, you'd be able to put them back in order. So that was how computation existed for a period of about 15-20 years. Then we start getting into computer. We get the invention of the cathode ray tube, right? We get the invention of the computer monitor, and once we had monitors, we could have information displayed. And basically, at some point, someone was like, "Oh, what if we hooked up a typewriter to a computer that had a monitor, and then we could type and see stuff on the monitor?" And then everything else was history. The reason we have the QWERTY keyboard layout for computers is because that was what typewriters had, right? And typewriters predate computers by a reasonable amount. So, once we had typewriters hooked up to computers, we could enter character keys into computers, and then we could see, we could write things into computers that enabled us to have programming languages as we currently know them. Python, this guy right here, this is an inheritance from the age of typewriters, right? And it's interesting, actually. If you once we get into characters, you'll see that there are some historical holdovers from the era of typewriters that are still existing in computers today. So as we go on through the 1960s and 70s, we start getting languages like ALGOL, Pascal, C. The C programming language was invented in the 1970s and is still in, reasonably heavy use. C is used primarily for operating systems and very basic stuff that has to run fast. That's one of the advantages of the C programming language, is it runs fast. These days, you've got all kinds of stuff like, Mark, what's the name of that code block language where people click and drag code functions together and click them together like they're Lego pieces. I forget what the name of it is, but graphical languages. So in general, graphical languages, they're gaining some popularity in the educational sphere because, the Lego analogy makes it easier for kids to learn how to program. But generally speaking, real programmers don't use that kind of stuff because it's just faster to type. And at a certain point, it does come down to speed. That's the only reason people still use command line interfaces, is because typing on a keyboard is faster than finding the icon and clicking on it inside of like a graphical user interface. So textual programming languages are still dominant, overwhelmingly dominant for large programs and programs that are sort of used in real-world circumstances. So that's why we learn stuff like this. Okay. I know I've been talking reasonably fast. And I know this is a lot of information to throw at you all at once, but scratch! There we go. Cool. So you might be saying, okay, so the professor has said CPUs have a small number of commands that they actually execute, and he's also said that each line in Python corresponds to a number of these commands. Okay, so there must be some process by which Python becomes CPU commands. In a conventional programming language, that's known as the process of compilation. You compile a program, and it becomes CPU instructions that may then be executed. Sort of from a black box perspective, a compiler is a program that you feed a program into it, and you get an executable, a binary executable out of it. You can then execute that executable inside of your operating system, and then it just runs. That's how a traditional programming language works. Something like C or C++ or Java. Or, well, Java has the Java virtual machine, so not Java, but C or C++ for sure. Python does things somewhat differently. The way that Python works is, although it's capable of producing standalone executables, generally speaking, how Python works is you open up the Python process, and it sort of sits as this like squidgy mass between your operating system and your program. Your program sort of sits on top of the Python process and is fed into it one line at a time, and the Python process itself interprets each of those lines of code as they're being fed in, and then sends them to the operating system to be executed. So rather than compile everything up front, how Python works is on a line-by-line basis. There are advantages to that, and there are disadvantages to that. In Python, you don't see a syntax error unless Python has tried to execute that line of code. So if you have a syntax error on a branch of your program that has never been executed or will never be executed, it doesn't show up. It won't, like the program will never hit it, so it'll never be a problem. This can be a bad thing because it's not good to have bugs in your code especially if you don't realize they're there. This is in comparison to something like C, where C checks the entire program for syntax errors as its first step of compilation, and if there is one syntax error in the entire program, the entire compilation process fails and you can't execute anything. Python will execute up to the point where it hits an error and then it stops. So that's an important difference. So compilers are a thing that enabled what us computer scientists call the fourth generation programming languages. That is a programming language that's not directly executed by the CPU itself, but exists in a sort of meta notation that is then CPU commands are then derived from. So in a high-level language like Python, you might have something like u is equal to u minus v. You can see we've had commands like that within this context. I is equal to 0, I is plus equals 1, something like that. In terms of machine language, you would first load R1 with u, then you would load R2 with v, you would subtract R1 from R2 and store the results in R1, and then you would store whatever's in R1 back in u. So you can see this very, very simple operation in C or Python corresponds to 4 CPU language instructions at least. Good. I think I'm just going to round out this set of slides, and then we'll take a break. Okay, guys? So let's talk about some engineering trade-offs. So differences between different programming languages. We have a few of them to go through. So in programming, we talk about the difference between high-level and low-level programming languages. The basic distinction between high-level and low-level programming languages is how directly the programming language itself resembles the underlying CPU instructions. So, or another way of thinking about this is how many CPU instructions are generated per line of code of whatever this language is. So, another way of thinking about it is how much can I accomplish in as few characters as possible. So, with programming languages like Python, R, and Haskell, R is a statistical package primarily, many mathematical abstractions are used, so you can write a heck of a lot in a very tiny amount of space. I would argue that Python is not as high level as something like Haskell, but, neither here nor there. At the low end of things, low level, and please understand that, understand that when a computer scientist says low level, that's not a judgment of value. That is a description of the position of that language within a sort of hierarchy of abstraction, right? High-level languages are highly abstract languages. Low-level languages are not very abstract languages. So low-level means very close to the underlying CPU level, which is the lowest level of abstraction. Although you could make the argument that the CPU itself is the, absolute bare, that's the rock bottom of abstraction levels, because there's no abstraction going on whatsoever, because that's the actual physical system, right? Anyway, so what are the advantages of high-level versus low-level languages? Generally speaking, it's easier to program in a high-level language, and your program will be faster in a low-level language. The thing about high-level languages is they often introduce all kinds of stuff that's not exactly unnecessary, but, roundabout, they introduce a lot of fluff. It takes fluff to enable the mathematical abstraction. It's easier for a human to program with this higher level of mathematical abstraction, but it's harder on the CPU. It takes more effort to do to support a high-level language from the perspective of the CPU. Whereas If you're speaking the CPU's language directly, it's a lot harder on you, the programmer. You have to have a much, much better understanding of how a computer works in order to be able to program like that. But the instructions you're giving the CPU itself are much more direct, much more directly applicable to the CPU, so they run super, super fast. So the traditional analogy, or the traditional example I give of this is, if any of you are familiar with the video game from the 1990s, Roller Coaster Tycoon, the first one, that game accomplished something that had never been accomplished before. It was groundbreaking at its time, because you could have like upwards of 1,000 of these little NPC guys running around your theme park, riding on your rides and doing all kinds of things and interacting with your theme park in a complex manner that's dictated by various hunger, excitement, thirst meters that are all individual statistics attached to individual characters. It was a vast amount of data to be processed by a video game back then. And it's still pretty impressive, actually. Like you look at video games from the you can look at knockoff video games from even the late thousands that weren't able to accomplish that level of that number of simultaneous NPCs. It's pretty impressive. And it came down entirely to the fact that the guy who programmed that game, Chris Sawyer, optimized that game in assembly language. So he went down to the lowest level of programming language that exists, that people can actually program in, and optimized that game in assembly. And because he did that, he could accomplish like vast feats of engineering because he'd optimized it so well. Interesting stuff. Anyway, so another difference that we commonly talk about with programming languages is the difference between application-specific languages and general-purpose languages. Application-specific languages are also often called DSLs, or domain-specific languages. Basically, the more specific the use, the more it's application-specific, or a DSL, right? So, for example, SQL is used only for databases. HTML is used only for web pages, and is also not a programming language. HTML is not a programming language. And R is used only for statistics, primarily. It's like, you could use these things for general programming if you really wanted to, but they're really not designed for it, and you'd just cause yourself headaches. So, it's like, you have a nail, and you want to hammer that in. You could use a wrench, you could use a socket set, you could use a reciprocating saw to do that, but you're depending on what you use to do that, you're likely to damage either yourself or the tool, right, in order to accomplish that task. It's much easier to use a hammer, right? That's sort of the design philosophy when it comes to application-specific languages. You should always, whenever you're embarking on a project, pick a programming language that is suitable for the project you're embarking on. Then, on the other hand, you have Python, C, Haskell, other general-purpose programming languages. These can be used for many, many different types of applications. In general, especially if you're talking about languages with well-supported libraries like Python or Haskell, C has well-supported libraries as well, but it's like everything's so low-level that, it's not going to make the point that I'm trying to make. In Python, you have lots of libraries that allow access to application-specific domains, right? So there are Python libraries that allow you to make databases, web pages, or statistics, or process statistics. The thing is that Python will never be able... Python can never be as efficient as a domain-specific language for any of these particular applications, but it can integrate things together that otherwise couldn't be integrated easily. It can do all kinds of interesting things, so that's why, that's what the purpose is in learning it. Cool. Yeah. Abstraction. Oh, that's a good question, actually. So, very briefly, abstraction means, it's actually kind of difficult to pin it down. Let's see what Google thinks. Abstraction. Define. So, the quality of dealing with ideas rather than events, or freedom from representational qualities in art. A little bit. So, when we talk about abstraction in a programming context, essentially, it's like hardware is a basic level. CPU language is a level of abstraction on top of hardware. So it hides many of the details of the circuitry, right? That's another way you can think of abstraction, is as a process of hiding detail. If you, for example, if you take a photograph of an orange, right, that presents a certain amount of visual information to you. If you take a cartoon or a clip art drawing of an orange, you can still understand it as being an orange, but it's an orange insofar as the most prominent feature of oranges have been taken out of the photograph and used to represent the orange in a more abstract manner. So that is kind of what an abstract programming language does to the CPU instructions. The CPU instructions contain a vast quantity of unnecessary detail. You're interested in only the sort of the outside edges of what distinguishes the program, if that makes sense. And when you program in Python, that it's like you're programming. It's like you're doing a cartoon version of the CPU program, which is the photograph. I don't know, maybe that's a bad analogy, but anyway. So I already talked a little bit about the difference between interpreted and compiled languages. Python is an interpreted language. When we run a Python program, we are running it inside of a Python environment. Whereas if you're programming in C, C is a compiled language, so the entire program is fed into a compiler all at once, and an executable is generated, and that executable can be executed by you. The advantage of interpreted languages is that they can be easier to debug, sometimes, and the advantage of a compiled language is that it is faster. So we have, in general, 3 different domains of programming language. We've got 3 different paradigms. There are more than this, but these are like the basic ones. At the top, we've got imperative/procedural languages. These are sequences of operations, sequences of instructions. Object-oriented languages are generalization of imperative languages, and imperative languages are used in this course and 1xC3. For all of the differences between Python and C, they are both still imperative languages. Declarative languages are things like Haskell. You don't say how to calculate something, you say what you want calculated, and you leave it to the compiler to do the calculation. In general, declarative languages tend to be higher level than imperative languages. You then also have logic languages, which are focused on reasoning about logical statements. Those are a reasonably rare case, and they're like the odd duck that doesn't really fall into either of the other categories. Although I might argue that they're if they're anything, they're a declarative type, but, if you take 1JC3, you will learn how to use declarative languages. Cool. Frozen again. How annoying. I wish I could figure out what's causing that. Cool. Again, it doesn't really, as long as you get the voice, that's the main thing, right? Anyway, so what distinguishes programming languages? What distinguishes something like C from something like Python? Well, the first and most obvious thing that distinguishes programming languages are the specific characters that are used to write the language. You know, we already talked about the difference between Python and C in terms of indentation versus curly braces. But there are lots of these tiny little differences. When you're trying to learn a new imperative language, having already known something like C or Python, you know, if you're trying to go from Python to C or C to Python, to some extent, it's like trying to play Bloodborne after having played Dark Souls. You have to just spend a certain amount of time learning what they've renamed everything, you know? You also have differences in safety, like type checking. So, in general, one of the things that compilers often do is ensure that you're using variables according to the types that have been declared for them. In Python, we don't really declare types. Everything is dynamic and loosey-goosey and terrible. In something like C, you have more rigidly defined types. So, you know, the program can determine for itself whether or not you're using things correctly, which ends up being very helpful to writing correct programs. So, you know, in this case, you know, something like Java supports like the strength of the type checking will vary by language. Is what I guess you're supposed to, what I'm should be saying here. There are various constructs that enable easier management of large programs. These are things like classes and exceptions and you know, functions and structures and all of these inbuilt abstraction mechanisms. The more abstraction mechanisms you have, the larger the program you can manage, essentially. So when you have languages like Java and Python that have large numbers of abstraction mechanisms, I would throw C++ in here as well, it's easier to write a program that's large. You can manage the program much more easily. In C, you lack many of those abstraction mechanisms, so it's much more difficult to manage a large program. A big difference between programming languages, and actually, to be honest, the reason most programmers will pick one language over another is the presence of libraries. A library is a pre-written piece of code that you can use that is distributed either for free or sometimes they're proprietary for a particular programming language. So Python, because it's a popular language, has a very large number of libraries that do all kinds of different things. You know, you've got libraries for statistics, you've got libraries for making graphs, you've got libraries for file processing, you've got libraries for, you know, artificial intelligence applications, lots and lots and lots and lots and lots and lots of libraries. The more libraries a language has, the more likely people are to use it, which means that, you know, it's sort of a snowball effect. Because the more people use it, the more likely they are to write libraries for it. You know, if you have a fairly small language that not so many people use, like, you know, OCaml or something like that, the fact that there aren't a huge number of libraries means you have to perform more work yourself. And if there's one thing that can be said about programmers, they are lazy. They are so lazy. If somebody has written a library, they will use that library before writing their own version of it 100% of the time. And that's actually correct. Like, that's the correct way to program, too. That being said, while you're learning the basics of programming, it's useful to re-implement things that have been implemented in libraries because you need to learn how programming works. But, you know, if you were working a programming job somewhere and you're not using libraries, you're probably not going to have that job forever. Let's just put it that way. Portability is another big thing, although it's, you know, less of a big thing these days. If a programming language can only be run on the Nintendo Switch, for instance, it's fine if you're developing a Switch game, but if you want your program to be distributed more widely than just that specific platform, you need to write it in a language that is portable to those other architectures, basically. So let's talk about Python. Python itself. Python is a general-purpose imperative slash procedural language. You can use it like an object-oriented language, but you can also use it like a functional language. It integrates some aspects of functional programming. It's therefore a multi-paradigm language. Although a functional programming purist, such as myself, would scoff at the idea that Python would consider itself a functional language. There is only one pure functional language, and that is Haskell, according to Haskell buffs, such as myself. Python is a high-level language, so it supports many types of mathematical abstractions and data types, which allows programs to be abstract and easy to understand, hypothetically speaking. It's like, in order to fully understand what's going on in Python, you need to have like a C level of understanding. A C, the programming language, not C, the grade level. Haha, dad joke. You need to understand the same sorts of things as you would understand if you were programming in C to really understand what you're doing in Python. But you can kind of get by in Python without understanding a lot of that stuff because Python has a whole heck of a lot of stuff, a whole heck of a lot of code that's built into it that allows you to not have to worry about memory management, for instance. But again, you can use Python more effectively if you do understand the memory management stuff. Python is an interpreted language. It compiles to an intermediate language, and then it interprets it. This makes playing around with the Python environment quick, allowing for easy exploration. The fact that you have a Python command prompt here, this is the Python interpreter. When I feed commands into the Python interpreter like this, essentially that is precisely the same thing as feeding a program like this in one line at a time. The disadvantage of using the Python interpreter is that you can't go back and modify previous lines like you could if you were modifying a document, which, you know, makes it tricky. Like, you got to get it right the first time if you're going to enter it into the interpreter directly. But the advantage is that you can just say something like 6 plus 7 plus 9, press enter, and you get the result. You don't have to, you know, there's no fiddling around with files. You can just enter commands. It's also really useful for, like, testing out a function to see if it works the way you think it does. I highly recommend playing around with the Python interpreter. Python uses compact and intuitive notation. Whitespace has semantic content, so you in a programming language like C, it doesn't actually matter where the whitespace is. Like, you could put on your C program on one line, and the C program, the C compiler would not complain at you. But with Python, you know, statements need to be on separate lines because they don't have semicolons terminating them. You need to use correct indentation for code blocks because you do not have curly braces. All kinds of stuff like that. Python is also very widely used in industry. Very widely used, actually. Programming language popularity. Where is it? Yeah, the TOB index. So the TOB index is a measurement of the use of programming languages sort of across the internet. What they're actually measuring is how much people Google how to use a programming language. So you can see that currently C is on top. It had a bit of a dip a few years ago, but it's back on top. Probably because it's still, like, the other thing to keep in mind is that the fact that these guys are taught in school is also, that's going to have an effect on this particular index. But you can see that Python itself is this black line. So you can see over the past few years, Python has seen increasing use, especially in the last 2 years. It's upped itself quite substantially. Java has been sort of in a slow decline. C has been relatively stable, except for that dip a few years ago. C++ has been sort of on the decline for a little while, and now it's stabilized. Essentially, what's been happening is the sort of properly object-oriented languages have been... Python has been slowly overtaking and consuming them. So, yeah. So yeah, this is an interesting website if you're interested in this sort of thing. I would say if you're looking for programming languages to learn for a, for a resume, this might be an interesting way to guide that. But I would say, assembly language is certainly not the 8th most or the 14th most used language, but it's perhaps the 14th most learnt language, shall we say. So there you go. Boop. So Python. Python was started in 1989 by Guido van Rossum from the Netherlands, who declared himself benevolent dictator for life of Python. So essentially, he established within himself veto power over any decisions that get made about the Python language. It is an open language. Every year they have a Python conference, and that they decide, whether or not they're going to include switch statements. Apparently, in the newest version of Python, they're going to include switch statements, which doesn't mean anything to you, but it means a lot to me. So Python 2 went out of date last year. It's no longer supported, so Python 3 is the correct one. Python is named after the British comedic sketch comedy group Monty Python's Flying Circus, which, if you've never seen the show, it's a riot. Highly recommended. So, yeah. Anyway, that's topic 1. Let's see. What did I code my video game in? It was Unity, so C#. C# is kind of derivative of C++. Well, it's C# actually. C++ is, Unreal Engine uses C++. You should not plagiarize, no. Yeah. Thank you very much, Mark, for being here. Yes. So, we're going to call a break. Quick break, 10-minute break. We will resume class at 10:50. So, until then, my friends, until then. So I look, yes. With respect to how many different C derivatives are there, what Mark's talking about here with Objective-C, C#, and C++, these are like, these are, I would say, the direct members of the C family, shall we say. Whereas the ones that David is talking about here, these are all like C derived, but like are done by people other than the C people, basically. I think Objective-C is actually in that category as well. I don't think Objective-C was done by the C guys, if that makes sense. But so the problem with C, the problem with, you know, counting who and who is not, oh, you don't like classical music? Too bad. I like classical music. My stream, my rules. Sorry if that sounded a bit harsh. What was I gonna say? Yeah, so C was so enormously popular in the 1970s that, like, and the 1970s were such a pivotal moment in the history of computation that it's impossible to see, so to speak, a programming language that doesn't have C influence. You know, and it's, you know, in the same way, you know, C itself was influenced by earlier languages, but, like, its huge, like, the huge popularity of C in the 1970s, like, within the space of programming languages, if programming languages were the fantasy genre of fiction, C would be the Lord of the Rings. That's the level of influence you're talking about here. So, you know. And the manner, like, the way that C managed to acquire that level of, is that it was one of the first languages that was designed universally for lots and lots of different architectures. Because it was sort of compatible across many different architectures, it gained a great deal of popularity in a time when there were a large number of very different architectures that were on the market. And, you know, that's sort of how it gained its popularity. And, again, learning C is an extremely useful thing to do. But, anyway, so let's continue on. And let's talk about, yeah, I know. Let's talk expressions. So, I'm going to be doing a fair amount of this in the Jupyter interpreter, the Python interpreter. So if you have downloaded the Anaconda distribution, or if you just open up a Jupyter notebook, like if you've gotten Anaconda, please feel free to follow along. Type along with Nick, as it were. So, we can use the interpreter directly to do arithmetic, right? So, we've got plus, we've got minus, addition, subtraction, we've got multiplication, we've got division, we've got a different type of division that we'll talk about, and exponentiation is a, there we go, exponentiation is a double asterisk. So that's kind of cool. Not all languages give you an operator for exponentiation. Sometimes you have to call a function to do this. So that's kind of nice. So So we need to draw some distinctions now, because, in regular arithmetic, you define the difference between numbers and operators, right? 6 is a number, negative is an operator. I'm not saying anything you didn't learn in grade school. Inside of a programming language, we still call basically everything is an object, but they have different categories of object, right? So everything is an object. This is object-oriented programming, right? So operations are objects. Functions are objects. Numbers are objects. However, when we talk about numbers, what we're talking about specifically are literal scalar objects. Normally, I will just call them literals. Object, everything is an object, so it's almost like, if everybody wins a trophy, nobody wins a trophy. That's kind of the category you're in when you're talking about objects in an object-oriented programming language. It's not, to some degree, it's not even useful. Although it is useful to understand that they all share some certain properties as objects. Scalar means it's indivisible. It's not comprised of subcomponents. 6 is 6. There's no breaking 6 down into anything else. It is just 6. It is a sequence of ones and zeros that constitute the number 6. Literal means that it represents directly in our source code what it claims to. It's not the result of some other operation. So we might say, let's define a quick function. Define add 3 x, y, z. Return x plus y plus z. Very quick function, right? Add 3, 4, 5, and 6 yields 15. So it goes. This guy, I know this isn't true with respect to the operations themselves, because, we're stepping into things, but from the perspective of the composition of an expression, this guy right here, add 3, 4, 5, 6, this is a scalar object. It's treated like that. So, as opposed to 3 plus 5, that's an object, but it's not a scalar and it's not a literal, right? You have to perform different operations to get there. I don't know. The thing that I'm trying to say here is, at this function call can be used inside of an expression, right? So when you write an expression, anywhere I've used a number here, you can actually substitute another expression recursively. Recursively just means, you can do the same thing again, but, slightly smaller. So function calls, the results of function calls are, like, when you call a function within an expression, the computer steps into that function, calculates the result, then substitutes that result into the expression as the final step. And then it continues to calculate the rest of the expression. So, we can, add 3 plus add 3 with different parameters. We can set a variable. We can use that variable multiple times. We can mix, we can match, all kinds of fun stuff. So, let's see. Oh, okay. Okay, sorry, Sonia. Could I share what piano song it is? Right. You know that meme of the "Hello, fellow young people" meme of that guy dressed like a 90s skateboarder? That's what I feel like right now, because that is internet slang. So the piece in particular is Piano Trio Number 7 in B-flat major, Op. 97 by Beethoven. There you go. I thought that Beethoven was relatively inoffensive. Okay, so anyway, moving right along. So you may notice that you may have noticed up here when I used two different types of division. In one case, I got 4.0, and in the other case, I got just 4. What we have subtly introduced is the difference between integers and floating point numbers. So integers operate in the same manner that you would expect them to, given your familiarity with mathematics thus far. So integers are whole numbers, positive or negative, including 0. Normally in a computer, you have limits on the size that an integer can be. It's sort of bound to the word size of the operational memory unit of your system, normally 64 bits these days. But in Python, they do a lot of work in the background so that you can have an integer that's as large as you like. So we can calculate really large numbers in Python, like that, hypothetically. Yeah, there's a big number for you. So normally, a computer program would flop out on that calculation, but you notice how it took some time though to calculate that. Python will do it, but it'll be slow. That might not seem slow to you now, but it is slow. So that's integers. Whole numbers are integers. So the other one is floating point numbers. Floating points are real numbers. They're a little bit complicated how they're actually stored in memory. It's like scientific notation, but in the binary system. That's the way that floating point numbers are actually stored. And floating point numbers, they do not have perfect precision. So it's kind of interesting. We're going to discuss this a little later on. But if you have floating point numbers like 0.1, 0.1 isn't actually 0.1. It's a number that's very, 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 very close to 0.1. And if you add 0.1 together a bunch of times, you'll see something cool happen. So that's 5, 6, 7, wait, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, if we add 0.1 together 10 times, the result should be 1, correct? Incorrect. Inside of a computer, each one of these guys is actually very, 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 very slightly less than 0.1. If you add a bunch of these guys up, the error accumulates and eventually becomes visible. So, you know, if you can work this back to determine the particular point at which the error accumulates enough to be able to see that. So it's actually 8. So yeah, floating point numbers are necessary because it's necessary to be able to represent real numbers inside of a computer. But they're tricky. They're not to be trusted. You should never trust floating point. You should always take measures so that, you know, it's like you're at a dinner party with a relative of yours who you know is going to eat all of the brownies, so you save some brownies in the fridge so that when this relative eats all the brownies, there are still some brownies for everyone else. That's the way that you have to deal with floating point numbers. Yes. So, operators can be applied to objects to form expressions that yield other objects. Yes. So, when you perform 6 plus 7, the result of 6 plus 7 is an object that can be fed into further calculations. So, for example, if we want to do our add3 function again, we can actually put expressions in as the arguments to that function. This works because the result of this calculation is something that's valid as input to the function add 3. Cool. So you can mix and match like this. It's really cool. Interestingly enough, a lot of people think something like -7 is a literal, but what that actually is the negative unary operator applied to +7 to yield -7, quote unquote. So -7, might not actually exist. It depends on the implementation. So, if you're interested to learn what the type of something is, Python has a very handy function built in called type, which allows you to inquire of the exact, what a thing is. So if we ask for the type of 6, it's an integer. 6.2 is a float. Add 3, 4, 5, 6, that is an integer, so it returns an integer. But if we make one of those a float, it returns a float. So that's one of the interesting properties of floating point numbers. If you add an integer to a floating point number, your result will be a floating point number, regardless how many integers you might have in a series of operations on floating point numbers. Float will be the eventual result as long as there's 1 in there. It's sort of float contaminates your otherwise perfect integer expressions. And also interestingly, the type of add is function. So add itself can be, just the function name can be used as an object in certain circumstances. Doop. On your Mac, actually, if you open Terminal and type Python 3, you probably have it already. You probably don't even have to download Anaconda to get it. So, here are your binary operators on integers and floating point numbers. You have addition, subtraction, multiplication, integer and floating point division. Very important distinction. We have modulus, and we have exponentiation. So, and in general, all of these follow BEDMAS order of operations rules. 3 plus 8 divided by 2 is 7, right? Whereas 3 plus 8 divided by 2 is 5.5. BEDMAS. So what's the difference between integer and floating point division? Well, let's imagine we have a division calculation we need to make that won't come out evenly. So 9 divided by 4, for instance. Using floating point division, we get a floating point number as a result. If we use integer division, we get an integer as a result. Now, it's important to note here that what's going on and what's not going on. The sort of decimal component here is being dropped entirely. This is not a rounding operation. Technically speaking, this is what's known as a truncation operation. You're sort of chopping it off at the decimal point and letting the tail fall off into the river. So, for example, if we have a number that comes out like this, would be rounded up if we were rounded, right? 5 divided by 9 is 1.8. The 1.8, if we were rounding, would become a 2, but under integer division, it actually becomes a 1, because we're not rounding, we're chopping it off and throwing it away. Truncation. So there you go. Another way of thinking about integer division is if you think about long division, where you have the remainder and the division, the result of the division. Yeah, I'm still going. Okay, good. When you do long division, you have the answer remainder x, right? You have x remainder y. Integer division is x. Modulo is remainder y. So modulus, or modulo, is the remainder of integer division. So if I have 9 mod 5, I end up with 4, right? 3 mod 2 is 1. So essentially, if you were performing whole number division, the modulus is how much the remainder would be. Modulus is it's actually an extremely useful operation. Modulus allows you to calculate recurrences. It allows you to determine the evenness or oddness of a number. We're going to get into it, but it's very useful. And it's also a thing that you actually probably need to put some effort into learning, because that's the type of thing I ask on tests. And I don't say use modulus operator to do X. I give you the situation, and you have to know that modulus operator is the thing that would most appropriately solve the problem. That's how that works. So, I see I got ahead of the slides a little bit today. So in general, BEDMAS rules apply to the expressions that you create in programs. If you want to be ultra safe, just add brackets to make it explicit, right? I know I'm terrible for this. Like, when I'm actually programming, I will have expressions that have, like, 8 and 10 parentheses in them. Like, you should see some of the stuff I did for my thesis, man. It is wild numbers of parentheses. Of course, I'm doing things in Haskell there, which is like a derivative of Lisp, and Lisp uses parentheses for everything. So, you know, Lisp, L-I-S-P. List processor. Old programming language, very venerable. Still used in some things, but anyway. So, we can use different types together. The only reason we can use different types together is because at some level that behavior has been defined. But again, if you multiply a floating point number by an integer number, even if that number were to come out evenly to a 0.0, it's still a float. It's like, okay, so how if you want an integer and you have a float, how do you do that? You perform an explicit conversion. So you can convert an integer to a float and a float to an integer by going int 3.6. You can see that performs the same truncation that that is performed during integer division. In fact, another way of doing that would be to use integer division by 1, I guess? That doesn't seem to work. Anyway, never mind. That doesn't work at all. So, never mind that bit. If you want to convert an integer to a float, you use float as a function name. Cool? Cool. Yes. So much for basic operations. You can also access sort of your extended set of operations. Things like trigonometric functions, logarithmic functions, you know, things like pi. If you want to access these types of extended things, you have to import the math library. The math library is a standard library in Python. It gives you access to, you know, math.cos, math.pi, stuff like that. You know, negative pi, exactly, divide by 2, very, very close to 0 without being 0, note. Yeah, so if you want these types, basically if you want a mathematical function that does not appear to exist, you should what you probably need to do is just import the math library. So that's operations. Cool. variables. So I've used the term variable numerous times. I've used variables, but we still haven't, like, examined or interrogated what a variable actually is. Although, I think I did say it. I did give this analogy last time in class. Variables in programming are different from variables in algebra. In algebra, variable means this could have many values. The purpose of many algebra problems that you would have done in high school and in elementary school is to solve for x. That is to say, you need to use mathematical reasoning to come up with a concrete value for this variable, and that is the problem, right? In computer science, or in computers, in computing, in programming languages, variables always have a fixed concrete value. Well, not fixed, sorry. They have a, well, it's fixed until you change it, shall we say. Variables in programming languages have concrete values. The correct way to think about it, the correct way to think about a variable is as a box that has a number in it. The box always has a number in it, and that number stays in the box until another number is put into that box, right? So in Python, these boxes sort of vary but in size depending on what you put into them. In other languages like C, the size of the box is declared up front when you create the variable. In Python, you create variables more or less on the fly. So x is equal to 7, x now exists, I can access it. If I ask for a variable that does not exist, if I ask for a box that nothing has been put into yet, I get an error, name y is not defined. You can't read something you've never written to, basically. So very often when you're writing a program, it is extremely useful to name variables according to their use and purpose. So, you can imagine if I had x is equal to 5, y is equal to 8, and z is equal to x plus y divided by 2, the fact that I was calculating the area of a triangle is not obvious from this, right? However, if I named it base, height, and area is equal to base times height divided by 2, that makes it much more clear what I'm doing. This is like a documentation thing. Documentation is extremely good, an extremely good thing for you to get in the habit of doing. It's like leaving information in the program about how the program is supposed to work and like what it says. So yeah, variables. Let's see. Do we have any questions? Cool. So, yeah, so variables. Again, if you think about how things work in Python tutor with, named boxes, that's, again, a good way of thinking about variables. So there are some constraints on the manner in which you name variables, but largely the name of a variable is something you, as the programmer, determine. So variables can contain uppercase, lowercase letters, digits, and the underscore character. However, they must not start with a digit and must not be one of the reserved keywords of the Python programming language. For example, if, def, while, return, import, global, etc. If you want to see a full list of them, you import keyword, and then you take a look at keyword.kwlist. These are all of the things you're not allowed to call a variable. You know, because obviously if you name a variable if, if you then entered an if statement, what do you mean by that if? Do you mean the variable, or do you mean an if statement if? It's ambiguous. So in order to prevent that ambiguity, the programming language is just like, you know what? You're just not allowed to call something if. You have your if naming privileges revoked. So there you go. The keywords are false, none, true, and as, assert, break, class, continue, def, del, elif, else, except, finally, for, from, global, if, import, in, is, lambda, non-local, not, nor, not, or, pass, raise, return, try, while, with, and yield. So there you go. We've got yield, but we don't have stop. Assignment. So assignment over literals doesn't make any sense. It doesn't make any sense to assign the value of 8 to 9. And that is a syntax error. Can't assign to a literal. However, the process of assignment over a variable is the storing of something in the box, right? So I can say x is equal to 9. I'm saying I am taking the literal value 9 and I'm storing it in x. The number inside of the box that constitutes x is now 9. If I ask for x, I get 9. There you go. Incidentally, the double equals means, is this equal to the other one? So is x equal to 9? True. Is x equal to 7? False. And these can be used within if statements to control the program's flow. So there you go. We also have multiple assignment, although this is something you're unlikely to use very much. If you have two variables, x and y, and you'd like to assign two different values to them, you can just do that all in one line by using commas. X gets the value 6, y gets the value 8. So an interesting illustration of how variables work is the swap operation. So let's imagine we have x and y, and we want to replace the value contained by the value that x has with the value that y has, right? We want to switch them. We want to swap them. And believe it or not, this is actually a memory operation that goes on inside of algorithms like sorting algorithms quite frequently. Swapping values in a sorting algorithm is actually one of the principal operations that go on. So the naive way of doing this is x is equal to y, and then y is equal to x. Right? So the problem with this, though, is that if we take a look at x and y, both of them are equal to 8. So, what gives? Let me just set x back to 6. So, in the first operation, when we set x equal to y, x is 8. Y is still 8. If we then assign y the value of x, we're giving y back the value that it had originally, which means it hasn't changed. So if these two statements executed simultaneously, then you might get what you expected from this swapping operation. The problem is, of course, nothing operates simultaneously inside of a computer. That's one of the corollaries of the fact that you run through a program one statement at a time, right? If you run through a program one statement at a time, no two statements inside of a program are ever executed at the same time. They are always done sequentially. So the way that you actually swap two values is you have to designate a temporary space in memory to store the intermediate value. So we say temp is equal to x is equal to y, and y is equal to temp. If we then take a look at x has the value of 8, and y has the value of 6. So you have to take that value, store it in some third location, then perform the perform the move, and then move from that temporary location into the place you were moving from. Cool. In Python, you can perform a swap using multiple assignment. So you can also just do xy is equal to yx. And then x and y have swapped their values. It's important to recognize when Python is doing extra work for you and when it isn't. This is a case where Python recognizes this construction as a swap operation and is assigning the temporary variable itself without, like, it's doing this work for you. It's not that this is, this is not equivalent to that, right? This is equivalent to this. It's equivalent to the version that uses the swapping variable. However, it just doesn't tell you. And you don't have access to the swapping variable. It just kind of does it in the background. So I always find it's important to understand what's going on under the hood with these things. Cool. So, again, I touched on this in a previous slide, but it's very, very useful to name your variables things that are useful. You can even have, like, fairly long variable names, like the degree to which people enjoy Skittles equals 8.2, right? There's nothing wrong with naming a variable like this. Nothing inherently wrong with it, although, everybody who's like a real programmer in the audience is probably cringing as I write this. But the cringe comes not from the fact that, this is not a descriptive label. The cringe comes from the fact that anytime you want to use this value, you have to write this whole thing out. So there's a trade-off between speed of typing and descriptiveness of what you're typing. Most people who are sort of experienced programmers will fall into the habit of making their variables very short and not descriptive. For people who are first learning how to program, longer and more descriptive variables are preferable. I would say they are preferable even for people who know what the heck they're doing. It's just people often fall into the habit of using very short variable names. Also, sometimes it's useful to indicate the type of the variable inside of the variable name itself. So if I were to say radius in float, that might be a useful thing to do. Or, money in integer form, stuff like that. It's useful to have naming conventions. We don't have to worry about it too much just yet, but just keep that in mind. So let's talk about comments. So, this kind of leads into the idea that there's more information necessary for understanding a program than simply the encoding of the instructions. Reading code is a difficult thing to do at the best of times, especially if it's not code that you've written or it's code that you wrote some time ago. In general, naming your variables usefully is helpful. What's even more helpful is leaving comments in your code. So, a comment is just a line of code that is never executed, right? It doesn't have to conform to the syntax of the language. You can just write sentences, right? What the comment character does is it tells the compiler or the interpreter to ignore this line, or ignore everything past this point. So this is a comment. So normally you want to comment things like functions, you want to comment things like functions with a description of what they do. So, for example, calculates the minimum and maximum of a series of numbers. Right? That's a clear, plain English description of what this function does. What it's applicable to is described in the by the placement of the comment within the code. You can do things like go to the top and author Mr. Moore. You can put descriptive information about copyright into code at the top of a file using comments. It's extremely useful to comment. Good source code includes lots of comments. Just comment. Comment your code. Comment your code. Comment. Just do it. I'm trying to hammer that home. So, yes. So comments are part of what we largely refer to as documentation. Documentation is extremely helpful and is a requirement of many positions that you would hold if you were to hold a position programming. Yes. Okay. So here's a joke. This is a joke. Documenting your code is like sex. When it's good, it's really good. And when it's bad, it's still better than nothing. So document your code. Even documenting your code poorly is way better than not documenting it at all. Yeah. So if we were to if we were to write comments on the something that calculates the area of a rectangle, it's like formula to calculate area of a rectangle, descriptions of both of the variables, and there you go. Comments. Cool. So, let's talk about Booleans. Am I still on? I'm still on, surprisingly. Okay. So we've talked about integers and floating points. These are both basic data types. Let's now talk about Boolean values. So we talked about Booleans very briefly, but essentially a Boolean can only have one of two possible values, true or false. So true and false are capitalized, so x is equal to true, y is equal to false, true, false. Boolean is that's the data type underlying the comparisons that are performed by both if statements and while loops. So if true, print this will always print, else print this will never print. Right? So if true, it does, like, the way that an if statement works is whichever, if the condition comes out true, then it does the first one. And if an else branch is specified, then it will perform that else branch in the case where the first one didn't, right? Because this is true, there's no way it could ever be false. So this one will, the first print statement will always execute, and the second one will never execute. This is actually a really redundant series of statements. You could equivalently just have this print statement, and it would do the exact same thing every time. Yeah. Incidentally, this is called the octothorpe symbol. So let's talk about some operations. So in the same way that we have arithmetic operations that that allow us to perform basic arithmetic, we have logical operations which allow us to perform logical reasoning, logical arithmetic. So x is true, y is false. X is equal to y, false. So this is a test of equality. Do A and B have the same value? So, 8 is equal to 5, false. 8 is equal to 8, true. 8 is greater than 4, true. 8 is greater than or equal to 4, true. 1 is greater than or equal to 4, false. Etc., etc. So we've got equality, inequality operators, and a not operator. 8 not equal to 8 is false. This is the same in Python as using the not operation, the unary not operator. So, yes. So, it's important to distinguish between the double equals and the single equals. In Python, single equals is always assignment, and double equals is always equality. So, if you use double equals and you meant to use single equals, you'll just not get the assignment that you wanted, which, is a bug, but it's not catastrophic. If you assign within the context of an if statement, that's just a straight up syntax error. It'll tell you have invalid syntax. Interestingly, though, that's not universally true among programming languages. If you perform assignment inside of a if statement condition in C, it'll actually let you do it. And that's, unless the circumstances were extremely specific, that's probably not what you wanted. So just get into the habit of using double equals when you mean equality and single equals when you mean assignment, and everything will go swimmingly. Cool. So, functions. Let's talk about functions now. We're really ripping through this. This is awesome. Incidentally, how is the pace actually? Are you guys finding the pace of this lecture good? You guys following? I would like to solicit feedback from the audience. I'm going through the code a bit quick. Okay. Okay. Cool. Well, if you ever need to, because this is a YouTube live stream, if you ever need to sort of rehear something that I'm saying as I say it, all you have to do is run the video back a couple of seconds, and then you can follow through with it. You'll just have a couple of seconds delay. That's possible in this format. It's not possible in Teams. That's one of the advantages here. Good. How do you take proper notes for this course? I don't know. That's up to you. Generally speaking, I think following along and like trying the operations as I'm doing them would probably be much more useful than like, you know, writing all kinds of stuff down on the slides. But, you know, you do you. I'm not going to tell you how to interact with the lecture. My primary function is to deliver the material. So there you go. So, oh, that being said, actually, I'd like to solicit for a note taker designation for this course. If anybody is taking notes and, you know, doesn't mind sharing those notes with some of the people in this class who need that kind of support, oh, I'm frozen again. If you wouldn't mind sending me an email about it, we can. I've received some requests that we designate a note taker for this course. So if anybody would like to fill that position and help out one of their a few of their the classmates with that, please get into contact and we'll make that happen. Cool. So anyway, functions. We've been using functions. Functions are extremely useful. They're a way of grouping together a sequence of operations under a common name so that it may be referred to multiple times in the future. You should think of a function as a unit of abstraction. So when we designate a function, we can have, you know, as many operations in that function as we want. But, you know, when we call that function, that's just one function call in whatever expression we call it in. So that allows us to insert vast quantities of code into expressions in other parts of the code, which is an extremely useful thing to be able to do. This is the syntax for declaration of functions. I've used this several times in class already, so let's go through it. Functions are declared using the def keyword, def. You then decide the name of the function. If you're programming for your own benefit, you get to decide what the function is called in the same way that you get to decide what the variable is called. When you are doing an assignment for me, you must use the function name that is indicated in the question. The autograder will be looking for your function according to a specific function name. If you do not use the function name that we have provided, the autograder will not be able to find your solution to the problem, and you will get 0. And we will have no sympathy past, like, the second assignment. Because by the second assignment, you should know this. So, after the name of the function, you then have a comma-separated list of inputs, parenthesis delimited. So, a good way to think about these guys is as variables that are declared upfront and given values by the call of the function. So, you know, up here, I have the add3 function, right? We defined add3 somewhere up here, you know, add3. When we give add3 3 numbers, you know what? I'll redefine it in here. There we go. Oh, that's the other really useful use of comments, is to just turn pieces of code on and off. So def add3 x, y, z print x is equal to x, y, and z. Copy and paste is the programmer's secret weapon. Find and replace is the programmer's secret weapon. And I don't mean copy and paste from other people's work. That's plagiarism. There. So, if we add 3, 5, 6, 7, Python 3, topic 1. I guess we're still on the topic 1, aren't we? Inconsistent use of tabs and spaces. What? I don't know what the problem is. Oh, I know what the problem is. It's complaining because I used both a space and a tab here. So that's a thing that you have to watch out for. Use tabs or spaces, not both. So notice when I call this function, the variable x gets the value that I called the function with, right? In that position. Y gets 6 and z gets 7. That's why when we print things out, it's 5, 6, and 7. Right? So these are variables that only exist while this function is being executed. So if I wanted to, for example, interrogate what the values of these variables are after the function has been terminated, you will see we get everything up to this point, but once we try to invoke this print function, name x is not defined. You may say to yourself, but it is defined. We defined it up here. That's not true. That's not actually the case. These guys only exist inside of this code block. Another way of saying that is that the x, y, and z are local to the function. So there you go. But I'm kind of getting ahead of myself again. You need the colon. In Python, anytime you have a new indentation level, there's a colon that precedes it. So you'll notice that that's true all through the the functions that we have up above. Then typically there is a return value. So the return statement designates the official output of the function. So if we print the output of add 3 with 5, 6, and 7, that is 18. If, however, we turn off the return statement by commenting it out, the return value is none. Even if we include x, y, and z here, it's like, there we go. Even if we put x plus y plus z here, because it's not been tagged with a return statement, we still get a return value of none. In order to actually return something, you have to use the return statement explicitly. And of course, when we mark your assignment functions using the autograder is looking for you to actually be returning something. So, you know, if you don't use the return function, you won't get any marks. That's the thing. Yeah. Man. My camera phone frozen again? No, it's good. Okay. Cool. So, yeah. So here's another example of a function. We have Pythagoras. So, let's just get rid of this bit. Def Pythagoras takes a, b, and or just x and y. So this will compute the hypotenuse of a right-angled triangle given sides x and y. And, you know, ordinarily you document that. Return x squared plus y squared to the power of 0.5. This is Python shorthand for square root. The other way that you do square root is by importing math and going math.squirt. Don't ask me why it's squirt. It always is, no matter what programming language you're in. Probably has something to do with the standard libraries. But in Python, you don't have to import standard library. You don't have to import math if you just raise it to the power of 0.5, because that is the same thing. Then, if we call Pythagoras on 4 and 3 and print the result, Mr., we get 5. There we go. So yeah, functions. Cool. So, here's another interesting little thing. For those of you who are used to algebra, the following is a thing that you do all the time, right? Generally speaking, in algebra, if you have a number and then a bracket immediately, that means multiply this by the contents of that, right? In Python, that's an error. Int object is not callable. So this is the syntax for a function call. Because 3 is not a function, it's an integer, it's like, I don't know why you're using an integer as a function, but I just can't figure it out, and it throws an error at you. If you want to do multiplication, you must explicitly provide the multiplication operator. That's a little pitfall for you. So, yep. I know it's actually square root. It looks like squirt, so I call it squirt. So tuples then. Actually, you know what? I don't know. Is it worth calling a break when there are 25 minutes left in class? Let's power through. So tuples. Remember back to the temperature example that we were talking about earlier today, right? This guy. This is a data collection. Python supports a number of different data collections. We're about to talk about one of them. The one that we're about to talk about uses round braces instead of square braces, and is called a tuple. Some people pronounce it tuple. I pronounce it tuple. You can pronounce it however you want, but tuple is correct. So tuples are collections of objects. They maintain their order. So if I declare a tuple, 1, 2, 3, 4, 5, 6, you can reference the elements of the tuple by position because they exist in linear order. It's a linear data structure. So the things that you put inside of a tuple do not have to be the same data type, so you can use integers, floating point numbers, Boolean values, and even things we haven't talked about yet, which are strings. Potato. There we go. So t at 3 is potato. You can put any number of things that you want into a tuple. There's no upper limit on the number of things that can be in a tuple. And no matter how many things there are, they will stay in the order you put them in. You can assign a tuple to a variable, as I did here, and then you can get at the things that are in the tuple using an operation called indexing, which is what I'm doing here. So, here are some basic operations on tuples. I already talked about indexing. It retrieves the I plus 1th element of the tuple. So again, data collections in computers start numbering at 0. That's because 0 is the first number. Actually, there's a real reason for it, and it has to do with memory addressing, but it's kind of beyond the scope of this course. Sort of. It's like, if you really want to understand why things start numbering at 0, you have to understand how memory addressing works, and you need to study pointers in C to get there, basically. And we're not going to cover anything like that in this course. So if you want to see that type of thing, take 1x C3 with me next semester. We need to boost the enrollment numbers to justify getting another TA. So that I can implement some gosh darn auto grading on that course, because, Anyway, miscellaneous tangents aside. So, T1, T3, T2. It's fairly common to write a loop that goes through all of the elements of a data structure like this. So if you start I at 0, while I is less than the length of T, print T at I, you get infinite ones, because what did the professor forget to do, like he tells everybody to do all the time? He forgot to increment his loop variable, which meant he got stuck in an infinite loop. Gets me every time. There you go. So, the elements in order are 1, 3.6, false, and potato. Hey, honey.
Yeah?
I just saw a delivery go to the door.
Okay.
We just got a delivery. Gotta stay on top of those porch pirates, am I right, guys? So yeah. So that leads us rather nicely into not this one, but this one, length of T. So this function is going to be one that you it's going to be one of those ones that becomes second nature to you by the end of this, because you're going to use it so frequently. This returns the number of elements in the tuple. The length of T is 4. Yes. Concatenation. If you want to take two tuples and jam them together and create one new big tuple, you use the plus sign, actually. So 1, 3, 5 plus 4, 6, 9 is just those things rammed together. This is not plus, this is not addition, this is concatenation. This should be a suitable introduction to you of the idea, the concept, that an operator will do different things depending on the data type that it's used on, or that it collects. So, in the context of tuples, this means concatenation. In the context of integers, this means addition. If you try to blend the two, you get problems. Can only concatenate tuple, not int, to tuple. Incidentally, if you just stick that inside of a tuple, then everything works out. If you want a tuple that contains only one object, you put a comma after that one object, because that is just an integer in brackets. That's called a singleton tuple. Singleton. So, we also have in, which is a inbuilt searching operator. So, is 3 in T false? Is potato in T? That's true. Reminding ourselves what T looks like. So basically, this will just look through all of the elements of the data collection, and if the thing that you're looking for is in there, it returns a Boolean true value, otherwise it returns a Boolean false value. We also have the inverse of that, x not in T, so potato not in T is false. Ta-da! Cool. So, am I frozen? No, still good. Still good. So, where are we? Yes, tuples. So, to answer your question there, where you should use spaces and where you shouldn't, if you're talking about indentation, you have to indent along the code blocks, right? Indentation must be code blocks. However, spaces within an expression, basically, they don't matter too much. So, for example, this operation is the same as this operation, right? Which is also the same as this operation. The only difficulty that you get into is if you tried to do, like, potato not in T, that the spaces separate the variable names and the keywords, so you can't use that. But with respect to, commas and operators like that, generally speaking, the spaces are optional and just for the purposes of readability. So, yeah. So, here are some interesting observations of tuples. Tuples are immutable. We cannot change an entry of a tuple once it has been created. So, we have T. Delete T. If we tried to say T at 1 is equal to 6, we get an error. Tuple object does not support item assignment. Once a tuple is created, it cannot be modified. This is the property of immutability. I already talked about that. Already talked about zero indexing. The first element of the tuple is T at 0, or whatever the name is. Right? So there you go. You can't set the values of things in the tuple once it's been created. So you might be saying to yourself, okay, sure, but why does this work then? I will show you. Let's say we had T, and we wanted to concatenate 1, 2, 3 to it. We would get the T tuple concatenated with this other tuple. However, the results were not stored in T. T itself was not modified. If you want that operation to modify T, you have to also include an explicit assignment statement. This is not so much the modification of T as the destruction of the old T and the creation of a new T, and the new tuple is placed in the place of the old tuple, thus destroying it, wiping it out, deleting it, overwriting it, etc. Cool. So, to your question, can you edit the inside of a list? Lists and tuples are different things. The primary difference between a list and a tuple is that you can do that to a list. So if we had a list, 1, 2, 3, 4, list at 2 is equal to garbage. That works. Lists are mutable. Tuples are immutable. You might be saying to yourself, why would you ever use a tuple then? And the answer is because they're slightly faster. This is the sort of stuff that we're going to get into topic 4, but that's a good question. Good question. So let's talk about strings. I introduced it a little bit when I talked about potatoes and garbage. So a string is a sequence of characters. They behave very similarly to tuples, but generally speaking, they are words. So if S is a string, we can say, hello, world. And S stores the characters HELLO, comma, space WORLD, exclamation mark. If you want to take the type of that, the type is string. Incidentally, type of T is tuple, type of L is list. So, strings, string literals can be used directly in your source code in the same way that I was using the tuple literal here. You can use string literals in your code. So if you wanted to do hello plus, come on, world, you know, you can use string literals in expressions. In Python, strings are either wrapped with double quotes or single quotes. It doesn't matter which one you use. Either is acceptable. The one caveat to that is if you want the string to include the double quote character, you can use the single quote, and if you want the string to contain the single quote character, you can use the double quote. For example, single quotes, hello, Carl. There you go. And if you wanted to use single quotes for that, you would do it that way. However, if you said to yourself, I'm going to use double quotes for all of that, essentially it takes this to be the beginning and the end of the string, that to be the beginning and end of a different string, and you have some operator called Carl in the middle, which doesn't make any sense, so it's a syntax error. So there you go, strings. I just completely anticipated the next slide. You can tell I've been teaching this course for a few years, eh? So there is one way of getting around that, and that's to use the so-called escape character. If you put a slash in there, you can get access to an extended set of characters that are kind of interesting. So that still works. So slash quote is a quote character. Just quote is, in a normal programming language, just quote is a string delimiting character. So in C, this is the way that you have to do it. So there you go. I know I'm making a lot of reference to C, but, you know, when I say this is how it works in C, you should in your brain think, okay, this is most languages other than Python he's talking about. So, boop. So what? So this sort of raises the issue that there are some characters, like not all of the characters that are bound on the keyboard are ones that you can use directly in strings. And this is true. So, in general, computers use what are called character sets, the most common of which is called ASCII. It was originally used on teletype machines, that is to say electric typewriters, and it dates back to the 1960s. In ASCII, in the original ASCII, each character is represented by 7 bits, so there were 128 possible characters in the original ASCII code. We have since extended ASCII to include, you know, characters that aren't in this list, essentially. So, you know, you'll notice that the only characters that are, I know this is really faint and pink, but here you go. The only characters that are in this list are uppercase and lowercase Roman characters or English characters, plus, you know, various punctuation characters and, you know, various brackets and things. You know, as computers became more widely adopted around the world, it became, you know, increasingly obvious that you're going to need more than just English characters. So the ASCII character encoding was eventually extended into something called UTF, Universal Text Format, or Unicode. Unicode characters represent, basically, there are so many, it assigns a lot more bits to the representation, right? Okay, let me back up. The way that ASCII works is that each character is a number. Each number is a sequence of zeros and ones. So it's a way of mapping numbers to characters. So when you write the letter A, right? That's actually a number. I think you can get it with ORD. Yeah. So this function reveals what the ordinal is of the particular of a particular character. So if you take a look in the ASCII table, A is in fact 65. If we wanted to do something like the @ symbol, that's 64. If we wanted to do something like bar, that's 124. So, you know, right there. And if you wanted to do, oh, let's see, is there something on this keyboard that is not in the ASCII table? Probably not. Maybe tilde? Tilde? Nope. All right. Well, suffice to say, if you pull in a character like an emoji or something, and you perform ORD on it, you'll get a number that's much higher than this, and that's because it comes from the extended ASCII set. So there are a number of interesting things in ASCII, like holdovers from the days when this coding system was used for typewriters. Like, for example, CR, ASCII character 13, is carriage return. Now, you know, if you've ever seen a typewriter, the way the typewriter works is you're typing, and as you type, the piece of paper you're typing on, you know, shifts left by a character space every time you type a character, and then eventually you have to press return, and it returns the page to its original position so that you can begin typing again. That's why it's called return, in case you didn't know, because it's a carriage return operation. So, you know, ding, typewriters. So a lot of these, you know, a lot of these command characters sort of date from that era. You also have interesting ones, though, like new line. So, if you print something that contains /n, hello world, this new line character is like hitting the enter key in the middle of a string. It pops things to the next line. You also have a tab character. So, this is 3 tabs over. There you go. So, yeah, basically. Let's see, any questions? No, you don't have to remember this chart. It's more like you should be aware of what a character is. You should think about characters as being coded numbers, right? Like, I'm just trying to get you to think about characters correctly, basically. You don't have to memorize this chart, don't worry. Again, like, if you ever want to know what the ASCII value of any particular character is, you can just use ORD, right? No, it's more important because you know, well, as you go on, if you use lower and lower level languages, you will find you have more and more cause to worry about the underlying ASCII encoding, so it's good to have an introduction to it in this course. Yeah, so Unicode currently has, well, this is probably a bit old, but it has north of 136,000 characters. They keep adding new emoji. You know, when they add new emoji, what has happened is a new emojum has been added to the Unicode specification. That's how new emojis come into existence. Yeah, so, yeah, anyway. All Python files are UTF-8 by default, which means that you can use arbitrary Unicode characters in string literals directly. So, stuff like my name is this Mandarin character. Hopefully this will work. U5F20. There you go. So the way that you access a Unicode character within a string is you do /u and then 4 hexadecimal digits. We'll talk about hexadecimal at a later point in time. But D83D. No? Okay. DE1C? No, okay. But you can see that, like, there's just a flipping lot of characters. Again, over 136,000 of them. And I already talked about new line. Rather than get into operators on strings, I think we can just call it there for today. We made excellent progress today. Thank you, everybody, for your time and attention. Let me see if we have any... If you have any questions for me, please put those into the chat. You know. TAs, just a quick constructive criticism of the manner in which things are being handled here. If you are a little more consistent about @ing the person whose question you're answering, that might make things go a little smoother. Yeah. Yeah, like, the important thing to know about characters is that they're not, like... You should never make the mistake of thinking that you're manipulating letters directly. You should always keep in mind that these are numbers underneath everything, and that you're, you know... You're still manipulating numbers, even though it looks like the computer's trying to fool you into thinking that you're working with characters directly. But everything underneath the surface is still, you know, like in C, in Python, you have to do it like this, right? Ord A plus ord 7. But in C, if you don't use the If you add 2 characters in C, what you are doing is you are adding their ordinal values, right? And you can also convert back to characters. Maybe. No? All right. Well, anyway. And you can also see it in hex. Yeah. Yeah, no, it's yeah, just take it as a constructive criticism. Like, please don't think that I don't super appreciate you guys handling these questions that are arising in the chat. Like, this is extremely helpful, and it's allowing us to, you know, you can imagine how long this would be taking if I had to answer all of these questions as they were occurring in the chat. And I think this is like very useful for you guys as well. So, you know, so be it. All right. Cool. All right. In that case, if there's nothing further, then I'm gonna go grab some lunch. Thank you very much for listening to me yammering on for 3 hours. Holy smokes. We're gonna get the assignments up as soon as possible. We're still working on getting the server together. They're not gonna be like you don't have to worry about any due dates until the week after next anyway, so don't worry about that. Yeah. I don't know. See you on Monday, I guess. Take her easy. Don't do anything I wouldn't do. Oh, and office hours. I'll be having office hours on Thursday at 10. Take her easy.